All right, hey everyone, welcome back to our series on linear algebra. So today we'll be talking about section 3.1. This is the beginning of chapter 3, and we'll just be talking about matrix operations. So everything that you can want to do to a matrix one way or another, that's what we'll be doing today. If you haven't already, I recommend reading through 3.0, the introduction to chapter 3. They pose some interesting questions and some problems to work on, and you don't need to have any prerequisite experience working with matrices or anything like that to solve them. They're really good intellectual exercises, and they kind of set the stage for this chapter. You can read that either before or after watching this video. But it's very insightful, and so I do recommend taking a look at that. So okay, and we have already seen what a matrix is, but I'll give a definition just so that we have seen it today. Okay, so an M by N matrix is a rectangular array of numbers called entries or elements, where there are M rows and N columns. So, uh, you know, this many rows and this many columns. Okay. Some notation, we generally call the entry that lives in row I, column J, Aij. Okay. And so in general, if we were to write down a matrix A, first of all, the notation that we like to use is this little this shorthand with brackets. We put in brackets and then the notation that we'll use to represent any entry in that matrix inside of those brackets. And so what this notation is saying is that the matrix A is the matrix whose entries are lowercase aij. So it's this matrix. A11, that's row 1, column 1. A21, that's row 2, column 1. And so on, all the way up to row M1, where this is row M, column 1. Then you go to column 2, in row 1, we'll have A12, and then A22, all the way up to AM2. Okay. The rows, of course, will stay the same, and what ends up in the last entry in the first row will be A1N, and then in the second row will be A2N, and so on. Down to the final entry in the bottom right corner is AMN. Okay. For example, well, something like this. 1, 0, 4, 2, 1, 1, 7, 9, -3. There's a 3 by 3 matrix, and the 9, let's just say that A32, the entry of this matrix in row 3 in column 2 is 9. Like that. It's this guy. Okay. Some other notation, if I don't know what this in general thing is. If A is 1 by N, if it is one row and N columns, then it's a column matrix or a column vector. Sorry. One row, wait, let me draw this. This is a row vector. It's one row, but N columns. So N entries in that row. So it's a row vector or a row matrix, you might hear. Similarly, if A is M by 1, then we have a column vector. Okay. And so you'll see matrices are kind of like generalizations of vectors. Okay, so we've been dealing with vectors, row vectors and column vectors for the last two chapters, and now we're upgrading to matrices. Let's just get some other definitions out of the way. This is a lot. So what we're going to do is talk about some more and more specific types of matrices that you might find. So the diagonal entries, these are the entries A11, the entries where the subscripts match. Oh, by the way, I didn't say it, but this AIJ business is called double subscript notation. Double subscript notation. I love double subscript notation, and I will use it as much as I can. Ah, that was exciting. A little bit of lag time. Double subscript notation, and yeah, I will use double subscript notation as much as I can. Okay, so diagonal entries are the entries where the subscripts match. That is A11, A22, A33, and so on. Okay. Um, if the matrix is rectangular, like not square, some tall skinny thing, it's these things or whatever. If your matrix is kind of flat, say 2 by 5, whatever, it's these guys where the row and the column match. Now, what if the number of rows is equal to the number of columns? Then we call the matrix square. M equals n. Yeah, the number of rows is the number of columns. I'll put that. Rows equals columns. Like number of rows. Okay. Now, a diagonal matrix is a square matrix where the non-diagonal entries are non-zero. Non-zero. Okay, let me give you an example of one of those. So, for example, 1, 2, 3 on the main diagonal, but zeros everywhere else. Right? Something like this. This is a diagonal matrix. A scalar matrix is a diagonal matrix where all of the diagonal entries match, or the same number. Are the same number. So, for example, 2, 2, 2 on the main diagonal. It doesn't have to be 3 by 3. It could be bigger, it could be smaller, whatever. And then an identity matrix is a scalar matrix where that number is precisely the number 1. A scalar matrix where the diagonal entries are 1. So let's just do a 2 by 2. 1, 0, 0, 1. Or if it was a 4 by 4, it would be 1s on the diagonal and 0s everywhere else. Yeah, it doesn't have to be 4 by 4. It could be n by n. Okay, great. So these words, we're not going to talk too much about today. We will, but next time we're going to talk. They're going to play an important role, especially the identity matrices. But for now, we'll just start learning how matrices themselves work as things that we can do operations on. So, for example, matrix addition and scalar multiplication. Um, Now, just like vectors were sort of generalizations of numbers, right? Numbers can be added and multiplied. And then we defined, okay, well, a vector is like a string of numbers that can be added and multiplied. And notice a vector of length 1 is literally just a number, and it has all the properties of numbers, right? Well, matrices are just like vectors, but with more rows, or more columns, right? If a single vector was like a column vector, a matrix is like 3 column vectors, a string, a row of column vectors, right? That's one way of thinking about it. And so the algebraic properties that matrices should mirror those of vectors, which mirror those of numbers, right? So for example, the ability to add and multiply. Okay, so I've written some cryptic symbols here. Um, we'll just talk about what they mean. So let A be the matrix Aij, which is m by n, and let B be the matrix Bij, which is also m by n. Notice, so both of these are m by n matrices, so they have m rows and n columns, just like before. What's important is that the number of rows equals the number of columns. Otherwise, what I'm about to define literally makes no sense. Okay, so what we're going to define is the matrix, which is the sum of A plus B. A plus B is the matrix whose ij entry is just Aij plus Bij. Notice it's an m by n matrix as well. An example, real quick. 1, 2, 3, 4, that matrix, plus, okay, I need something that's the same size. So 1, 1, 1, 1. What we're saying is that the ij entry, the entry in row I and column j, is the sum of that entry in A and that entry in B. So the first one will be like, this one will be like that guy plus that guy. 1 plus 1, 2. And then 3, and then 4, and then 5. In other words, addition happens component-wise. That's the main takeaway. And notice that was exactly the takeaway from vector addition as well. We add vectors component-wise. Okay, similarly, scalar multiplication. If I take a number, C, and multiply it by A, then what we're really doing is multiplying notice for vectors, same thing. What we do is multiply every entry by that number C. Okay, so for example, 2 times 1, 3, 5, 7 is, well, in every entry, just multiply that entry by the scalar, 2. So 2, 6, 10, 14. Just like that. Just like with vectors, multiplying by -1 is the same as like taking the negative of the matrix, right? You just multiply each entry by -1, but multiplying a number by -1 just is the same as taking its negative. So we write minus b for -1 times b, and in that way we can define matrix subtraction. If I had, let's just take these first two that we did in that first property. So if I did 1, 2, 3, 4 minus 1, 1, 1, 1, this will do exactly what you think. It'll give you 0, 1, 2, 3. Just subtract 1, whatever. Just go component wise. Subtract 1. Okay, these last ones, let me tell you what 0 is. You want a 2 by 3 0 matrix? Okay. It's a matrix of all zeros, and it is the additive identity. In other words, it's the matrix that you can add to A and get back to A. It's also the matrix that you get when you subtract A from itself. The matrix of all zeros, so nothing fancy. Oh, I did my examples on the side rather than at the bottom. But hopefully it's clear. We can do maybe one more. So for example, I don't know, 1, -1, 0, 2, 7, 7. Plus, 3, 3, 3, 1, 12, 9. Okay, sum of these two matrices, maybe pause the video and work it out yourself. But okay, 4, 2, 3, 3, 19, 16. And so on. Right, we just add component wise. Okay, great. Good, good. Right. Matrix multiplication now. Okay, so just like we had, remember when we defined the dot product of two vectors, we did something that was like not obvious. The one thing that it wasn't, okay, one thing we could have done was go and define the product of two vectors as like, oh, go component wise through the vectors, multiply each pair of components, and then make a new vector that's the same size out of those. Yeah, you could do that. But notice how useless that such a thing would have been in terms of application and how it's kind of not natural in terms of like what do we actually want the product of two vectors to measure. And then we had an entire section devoted to how useful this dot product was in terms of being a product of two matrices, two vectors. Well, here we have a similar notion of multiplying two matrices together. So it goes like this. Let A be an m by n matrix, and let B be an n by r matrix. Notice n, the number of columns of A, is equal to the number of rows of B. That's important, and we'll get to that in just a second. Okay? Then the product, C, which is like A times B, that will be an m by r matrix, with entries Cij, where Cij is this, which looks an awful lot like a dot product. It is a dot product. It's a very specific one. What you do is you dot row number I, okay, row number I of matrix A with column number J of matrix B. Row I of A is a vector dot column J of B. Okay, yeah. So what this is, right. Let me before I show you what that looks like, let me just point out one thing to notice about this. For that to make any sense at all, those two, the row, whatever row you're in for matrix A, has to have the same number of entries as whatever column you're in for matrix B. In other words, the number of entries in the rows of A, so here's A, 4 entries per row, I mean. For that to be dot product, for you to take a dot product with that in column B, it must be that the number of entries in column B adds up to the number, or is the same as that number of entries in row A. What that means is that the number of columns in matrix A has to be the same as the number of rows in matrix B in order for this to even be defined. If these numbers don't match up, the product is of those two matrices is just simply not defined. Yeah. And what will happen is the number of times you do this product, you'll do this dot product one time for each entry in the resulting matrix AB. Okay? So, so I've just drawn a 2 by 4 matrix, and then I've done a 4 by 3 matrix. Notice the number of columns in A matches the number of rows in B. I've highlighted two of the columns. So the two that I've highlighted are the first row and the first column. First row of A, first column of B. That will give me the 1, 1 entry in the product matrix. If I then do the second column of B, now I'm looking at the 1, 2 entry of the product, and then 1, 3, and then 2, 1, 2, 2, 2, 3. That second row will be done by doing the second row of A. Okay, let's do this with an actual example. Yeah, real example. So this one time we'll go slowly through what the product of two matrices will look like, and then after that we'll do a little bit shorter. So for dimensions, let's do nothing too crazy. A 2 by 3, so 1, 0, minus 1. I want to not be too unkind to myself, so let's do something like that. So it says 3 columns, which means the next matrix needs to have 3 rows, and we'll make it 3 by 3. So 1, 0, 0, minus 1, 2, minus 3, 1, 0, minus 2. Okay, this product. So again, the first thing we have to check is this is 2 by 3. This is 3 by 3. The way that I was taught to do this, just box in like this. And if the numbers inside the box match, then you're allowed to proceed. And if they don't match, stop now and just say product is undefined or it does not exist or something. Okay? We also know that the resulting matrix is going to be 2 by 3. So let's draw a grid, which is 2 by 3. Grid, I mean, like, we'll just put the brackets for the matrix first, just so that we know this will be 2 by 3. Okay, and now we systematically go and do dot products. Now, my preferred way of doing this is start with row 1 of the left matrix. Start with column 1 of the right matrix. I'm going to use highlighter for both of these, actually. Row 1, column 1. Okay, do a dot product. We can do this. 1 plus 0 minus 1 is 0. Great. Then do the second row. The second column of the right matrix. Where will that correspond to in the resulting matrix? Well, it's the first row and the second column. So it'll be the first row, and the second column. So it'll be right here. Okay, do the dot product. Looks like 0 plus 0 plus 0. This is going well. Maybe I made it too easy on myself. Okay, then do the third one. Looks like 0 plus 0 plus -1 times -2, which is 2. Okay. Now that we've filled out that first row, we can go to the second row. And we'll go one column at a time, right? This dot product looks like 4 minus 3, which is 1. And it will go right here. Then we do the next one, which looks like 0 plus 6 plus 0. It goes right here. Oops. And then the last one, of course, is going to go right there. It looks like 0 minus 9 plus 0. Final answer, and I guess you can get rid of the highlighter marks so that it's clear what the final answer is. 00216 minus 9. Great. Okay. Now, knowing this about matrix multiplication, we can talk about matrix equations. So look at the linear system: 4x plus 5y minus 6z equals 1, 3x plus y plus 0 equals 2, and then x minus 7y plus 2z equals 7. So that linear system, if we were to write it as a matrix equation, notice we could extract the coefficients in a coefficient matrix, but then go ahead and multiply that coefficient matrix by this weird column vector x, y, z. It's a column matrix, I guess, or column vector of indeterminates. Now, if you do the matrix multiplication, you have to go row by row, column by column, and so on. But there's only one column in the right matrix. And so you just take that column and multiply it by the 3 rows, and we're done. And each time you do, you get one of these left-hand sides of the expression. And so if we wanted to write the linear system as a matrix equation, we write it as a product of a matrix and a column vector, and then we set that equal to another column vector, right? That's actually true in general. This x vector is a vector of indeterminates that we're trying to solve for. And so if you have an augmented system, A augmented with B, that's the same as the matrix equation, AX equals B, okay? Oh, and by the way, I think it was theorem 2.4 that talked about that this augmented system has a solution if and only if B can be written as a linear combination of the columns of A. That's true of this matrix equation as well. AX equals B, okay? And now, also, this is not quite on the topic of matrix equations, but I do want to point out there's a way to extract any given row or any given column of a matrix. So let A be an m by n matrix. Let EI, which should have a vector on top. Oh no, I made so many mistakes. Let EI be a 1 by m standard unit vector. 1 by m means it's one row and m columns, so it's a row vector. It's a length m row vector, standard unit vector. So it's all zeros and 1, 1. Same for EJ, it'll be n by 1, so it'll be n rows and 1 column, so it's a column vector. And let that one be a standard unit vector. Then, okay, if you do EI times A, where multiplication is happening on the left, then what are you doing? You're multiplying every single column of A by this product, or by this standard unit vector. Well, if EI is the vector that has a 1 in the ith entry, then this will extract the ith row of A, right? Because just do the matrix multiplication, right? It'll look like this. You have a row vector times a matrix, whatever. And then we have zeros and ones inside of our row vector. So we take all the different columns of A, and each one gets dot product with this vector. But every time you do one of those dot products, all of the entries are going to be 0, except for the one entry that has a 1 in this thing, in which case you'll just extract that entry. 1 times that number is that number. And so every single time the output is just whatever the entry is in whatever row the 1 is in the standard unit vector. Okay, and so the output will be a 1 by n row vector for just as in terms of computing the dimensions of the output matrix, and it will be precisely the ith row of A, right? Okay, do the same thing with the jth column vector, but do the matrix multiplication on the other side. So, and this time EJ is a column vector, right? So it's got something like this. And so what we do is we multiply that column vector by each row in A. This column vector has all zeros and ones, whatever. And so what that will do is it will extract one of the columns of A, right? That's what the output is. It'll be, and not just an arbitrary one. It'll be the one column of A corresponding. It'll be the jth column of A, where the 1 is in the jth position of the standard unit vector. Okay, good. Another thing that we can do with matrices, we're just kind of, this is an overview, this video. So another thing that we can do with matrices is we can partition a matrix into a bunch of submatrices. We usually call those matrices, the submatrices, blocks. And so notice we've taken some 5 by 5 matrix, right? Okay, that's pretty big. And you may have noticed in our examples, we usually keep the number of rows and number of columns below, like less than or equal to 4. And usually not both simultaneously equal to 4. That's because after 4, you're not really gaining anything new. You're just gaining a lot of time spent computing things. It's like teaching 2-digit multiplication, like back in grade school, but or 3-digit multiplication. But at no point do we do 10-digit multiplication because that's just a lot of work. We can do 10-digit multiplication after we get the pattern with 2 and 3-digit multiplication. Yeah, same principle at work here. And in fact, once you get even in that analogy with multiplication of numbers, after a while you start to look for little tricks, right? When you're doing your multiplication, you try to simplify the computation, break it into some smaller multiplication problems. Yeah, that's exactly what we're doing here, partitioning the matrix into a bunch of submatrices called blocks. So if you look in the top corner here, this block is the 3 by 3 identity matrix. This block is the 2 by 3 zero matrix. And then these other 2 blocks are just 2 other random matrices. One is 3 by 2, the other one is 2 by 2. So we just call them B and C. So we can decompose A into a block matrix this way. You can do this partition however you want. And for what we're going to do here, we're actually, instead of this, we're going to do something like partition A into all of its columns. Something like that. Handy trick, although maybe not this particular matrix, right? Okay, let's do it. Partition B, which is an n by r matrix, into columns, okay? And then if A is an m by n matrix, so again, the number of rows of A is the number of columns of B, then we can do what's called the matrix column representation of the product AB. And it's a matrix which is partitioned by its columns, and every column is whatever corresponding column vector of B times the matrix A. Let me show you this. This is pretty fancy. So, right, we have A and B like this. A is 1, 1, 4, 0, negative 2, negative 1. B is 3, negative 2, 1, negative 3, 5, 0. And if we were to put A, B, well, let's partition B into its columns. 3, 1, 5, -2, -3, 0. Then AB is the matrix A times the column 3, 1, 5, and then partitioned with A times 3, 1, 5. The other column, -2, -3, 0. Like this. Now, it looks very fancy for a matrix, but what are we doing? Let's just do these matrix products real quick. So what is 3, 1, 5 dot product with A? Oh, multiplied with A, right? Well, it's 3, 1, 5 dot product with the first row of A and 3, 1, 5 dot product with the second row of A. So that first dot product is going to be 3 plus 1 plus 20, which is 24. And then the second dot product is going to be 3, 1, 5 dot with the second row of A, which is going to be 0, negative plus -2 plus -5, so -7. This dotted line is the same as this dotted line. And then we just do the second column of B multiplied with A. So -2, -3, 0 dot with 1, 1, 4 is -2 minus 3 plus 0 is -5. -2 times 0 is 0. -3 times -2 is 6. And 0 times -1 is 0. So this dot product of -2, -3, 0 with the second row of A is just +6. And we're done. You should check that this is the same matrix that you get with regular matrix multiplication. Although, if what we just did feels like just the definition of matrix multiplication, that's why we did this one first. As we did matrix column representation first as the first different way of approaching matrix multiplication, because it's the closest to the normal way that we do it. There's another one though, row matrix representation. So we'll do the same matrices, but row matrix multiplication takes the rows of A and partitions them. So we write A as A1, partitioned horizontally, all the way up to AM this way. So 1, 1, 4, 0, -2, 1 times 3, 1, 5, -2, -3, 0. What we do is partition the rows of A. Okay, and then each one gets multiplied by B. So the resulting matrix is going to be A1B, A2B. Actually, we know what A1 and A2 are, so let's write those as row vectors, right? It's 1, 1, 4, B, and 0, -2, 1, B. Like this. This is called row matrix representation. And notice, to compute 1, 1, 4 times B, we're just taking this row and multiplying it by each of these two columns. That'll give us a row vector of length 2. And it'll be 24, -5. You should check me on that one. I definitely cheated. Just scrolled up because we know what it's going to be. The next one will be -7, 6, right? 0, -2, 1 times the matrix B using matrix multiplication will give you -7, 6. Okay, great. So the outer product expansion If you remember, the dot product was called the inner product of two vectors. Now we know okay, so outer product expansion is the third one of these different ways of doing matrix multiplication. The inner product of two vectors is the thing that you get when you put a row vector times a column vector. Row times column. Well, now that's going to give me a 1 by 1 matrix, right? Because it's a 1 by n times an n by 1. And what you do is you do the dot product of the first row of this row vector and the first column of this column vector. That's just the dot product of two vectors, right? And it's just a number. And we get a matrix which is like one row and one column, and it's got one entry. That one entry is just the one the one number that's the dot product. Okay, anyway, right. But what if instead I had done this thing where I partitioned both the rows and the columns? Oh well, before we do that, let's just switch the order of this thing. What if I had a column times a row? Well, now, okay, I've got to figure out the dimensions of this thing. Well, notice this is a this is a 5, this is like 5 by 1. And this is 1 by 3. Well, the number of rows and columns still works out. So it'll work, but what is the resulting matrix size? Apparently it's 5 by 3. 5 rows, 3 columns. This. And each one is like this row times this column. Yeah? Okay, but like it's only just a product in that case. We just multiply the one. There's no like dot product of a row and column because each row and each column has just one entry in it. Whatever, in the right context. Okay, but if we upgrade that to general matrices A and B, such that, the rows and number of rows and columns line up, then what we can do is partition the the columns of A and the rows of B, and then just do the dot product one at a time. What that will do is give us a bunch of matrices, and then we just go and add those matrices together. What do I mean by that? Okay, let's do it real quick. So we had I'm going to make this a little bit smaller. 1, 1, 4, 0, -2, 1 times 3, 1, 5. Oops. -2, -3, 0. Okay. Now what we do is partition the rows, or the columns of A and the rows of B. And then we go, so now we have a bunch of row vectors and a bunch of column vectors, right? And the number of each of these is going to work out just fine. So, okay. So this is a one. So I've circled the two vectors now that we're going to multiply together. 1, 0 and 3, -2. But remember, on the left is the 1, 0 and it's a column vector, and on the right it's a row vector. So before you just go and dot product these two vectors, be careful, right? This is a 2 by 1. It's 2 rows and 1 column times a 1 row by 2 column vector. Draw the box. Okay, at least the inside numbers match. And so this product is valid. But what is the size of the resulting matrix? It'll be 2 by 2. And the way that we do the multiplication is we take each row of A times each column of B. So the first row of A, or the first row of the first column of A, times the first row of the first column of B is 3. Then the second row of the first column of A is 0, times 3 is 0. Then 1 times -2 is -2, and 0 times -2 is 0. Then go to the next row. All right, we just did the first one. Now we do the next one. Oh, right. Right. So A1, B1, then A2, B2, and so on, right? Okay, so now we do the next one. Again, this is still true. The size of the matrix will be 2 by 2. And notice, by the way, the final matrix that we've been getting every time is a 2 by 2 matrix. So at least the sizes of the matrices are working out correctly. But like this doesn't look like it's the right thing at all. It will be. So next we do 1 times 1 is 1. 1 times -2, right, is going to be -2. -3 times 1 is -3. And -3 times -2 is 6. Okay, and now we do the last row times the last column. I guess the last column times the last row. Okay, still 2 by 2. 5 times 4 is 20. 5 times 1 is 5. And then a column of zeros. When we do this, final answer, we have to remember now we have to add matrices together. Addition only works if the matrices are precisely the same size. Fortunately, all of these are 2 by 2 matrices, so we just add component-wise. 20 plus 1 plus 3 is 24. 0 plus -2. I have a minus sign missing somewhere. Plus 5 is 3. Somehow we've made that error at some point. Oh, our original matrix had a -1 in there, which didn't factor through. We should have a minus sign on this 5. -7. That's kind of cheating. Okay, anyway. -2 minus 3 plus 0 is -5. And 0 plus 6 plus 0 is 6. Okay. Very important. Great. Okay. So that's the outer product expansion. The next thing we want to talk about is powers of a matrix. This is more of a fun puzzle that I wanted to throw in there. This is actually a more general problem than the one the book has for powers of a matrix. Powers of a matrix just mean, so if I raise a to the m power like this, that means multiply it by itself m times. That's all. Okay? So we want to compute a to the m, arbitrary power of this matrix, the matrix of the n by n matrix of all ones. Okay. A to the 1. That would be a n by n matrix of ones. I'm not even going to write it. It's right up there. Okay, what about a squared? By the way, the strategy here, do the computation several times and try to find a pattern. That's the only way that we know how to do this. So that's what we're going to have to do. So a squared, that'll be, a times a. And because I don't have the tenacity to write that many ones, we're just going to do that. Okay. Now, what matrix is this? First of all, The insides match, so we're allowed to multiply. The outsides are both n, so the final matrix will be n by n. Right? And now let's take, so what do? We just do the multiplication. Take this column and multiply by this row. That'll give us this entry. You could do outer product expansion, I guess. Actually, that might be faster. But okay, don't take my word for it. Actually, no, they're the same. This is the same. Okay, if you do that dot product, notice each row and column is a row and column of ones. When you multiply a row or column of ones by itself, dot product style, it's 1 times 1 plus 1 times 1 plus 1 times 1 plus, yeah, all the way. How many times? N times. And so you're adding the number 1 to itself n times when you do a dot product. So the first entry is 1. Also, every entry is 1, is n. This is a matrix of n's. I'm going to use double subscript notation and say aij equals 1. So if I put, aij for this matrix equals n. I'm just going to put it that way. In other words, no matter what your I and j are, the entry is just the number n. That's strange. That's what it means to square this matrix. Let's cube the matrix. A cubed. Well, a cubed is just a squared times a. Yeah? So it's a bunch of n's times a bunch of ones. It'll still be n by n, is the final matrix form. Now, what is the dot product of a row of ones with a row of n's? Well, it's just 1 times n plus 1 times n plus 1 times n, and so on. In other words, you're going to add n to itself n times. That's n squared. N times n, yeah. And then n squared. Yeah? Let's just aij equals n squared. You know what we mean by this. If we then go and just put a 4 and a 3, do the next one. Well, now we just put squares on all these. Right? A to the 4th is just a cubed times a. And now what are we doing? We're adding n squared to itself n times. That's going to give you n cubed. See the pattern? And so our final answer is, if you were to do a to the m, it'll be n to the m minus 1 everywhere. N to the m minus 1. So you want to do this grid of ones raised to the 10th power. And if it's okay, and if the grid, okay, let's do an actual example. So let's do a 3 by 3 grid of ones, and then we're going to raise that to the 10th power. Okay, n is 3, m is 10, so it's going to be the 3 by 3 grid of 3 to the 9 everywhere. Whatever that number is, 27 cubed. I don't know. This is our final answer. That is a more general answer than we had in that is shown in the book. However, the book uses what's called proof by induction, and that is a very strong, sophisticated proof technique. If you're planning to take higher level mathematics courses like abstract algebra and analysis and like that kind of mathematics class, you will need to know how to do proof by induction. And this is the first time we will have seen it. It feels an awful lot like do the thing, a bunch of higher and higher cases, and look for the pattern of what you're doing each time, and then find a way to say it rigorously. If that's something that you think the future holds for you, I highly recommend looking at example 313 in the book, 3.13. It's a very good introduction to proof by induction. That's weird. Okay. And okay, because we gotta do it. Is another fun puzzle. We want to compute b to the 467, where b is this innocent looking matrix. Okay, as soon as they put a number like 467 in an exponent, you better believe something miraculous is going to happen, right? Did you ever have to take powers of the complex unit I? You take I to the 200 whatever. But you know that like, oh, wait a second, if I just do it a bunch of times, it just goes in a repeating pattern or something. This is going to feel like that. There's other ones like, oh, you could also predict that like maybe after taking enough powers, this matrix just becomes the zero matrix, and you multiply it by itself a bunch of times, you still get the zero matrix. Something like, we expect something strange like that to happen just at the outset of a silly problem like this. Okay, so let's do it. B squared. I'm not telling you to be square. Like, that's like being nerdy, and I would never inflict that on someone besides myself. Okay, b squared is this. 0 minus 1, 1, 0. I'll just write it again. Times 0 minus 1, 1, 0. It's a 2 by 2 matrix, so each one. And so the output will also be 2 by 2. We do rows of the first one times columns of the second. So I'm getting, when we multiply these, we get minus 1, and then beneath it will be 0, and then to the right will be 0, and then the last one will be this column times this row, so minus 1 again. That's interesting. That's a scalar matrix, right? Scales by minus 1. In fact, scalar matrix, it's called, a matrix is called a scalar matrix because all it does is multiply all the entries of whatever matrix that you're trying to scale by that scalar. So 0 minus 1, 1, 0 times the scalar matrix minus 1, 0, 0, minus 1. The effect of multiplying on the right by a scalar matrix where the scalar is minus 1 is going to just multiply all the entries of the first matrix by -1. So I'll tell you the output is going to be 0, 1, minus 1, 0. Now you should check that with normal matrix multiplication. I'm not going to do it here because we've done a lot of that already. B to the 4th. Well, that's going to be b cubed times b. So 0, 1, minus 1, 0 times 0, minus 1, 1, 0. Weird. What does this do? This, okay, let's just multiply them. Top entry is 1. The next one, the one beneath it is 0. The one to the right is 0. And the last one is -1 times -1 plus 0, which is 1. Again, check me on that one. Now that's the identity matrix, the 2 by 2 identity matrix. Now, for all the times you've heard the word identity in math, remember what it means. The identity matrix is the scalar matrix where notice it's a scalar matrix, but the scalar is 1. In other words, you multiply all the entry. This is the matrix 2 by 2, that when you multiply it by something that has 2 columns, it does nothing to the matrix. You get the original matrix back. So in other words, b to the 5th is just, b. I'll write it. I'll write it one time. It's 0 minus 1. Oh, sorry. 1, 0, 0, 1 times 0 minus 1, 1, 0, which is 0 minus 1, 1, 0, which is b. Yeah, this identity, multiplying by the identity, is like multiplying by 1. But hang on. That means if b to the 5th is equal to b, then b to the 6th is equal to b to the 5th times b, which is equal to b times b, which is b squared. But I know b squared. It's this guy. Right? Yeah, we've got a pattern here. Every 4 powers, we get back to the original. So in other words, b to the n is b to the remainder of n divided by 4. Think about that real quick. B to the 6 divided by 4 is 1 remainder 2. There you go, there's your 2. 5 divided by 4 is 1 remainder 1. Yeah? 45 divided by 4 is 11 remainder 1. So b to the 45 equals b to the 1. And so we just ask, what is 467 divided by 4? 464 is a multiple of 4. So 467, I don't know, 116. Remainder 3. You might want to check me on a calculator on that. Remainder 3. So b to the 467 is b cubed, which was negative b, which was 0, 1, minus 1, 0. Pretty cool. Takes an arithmetic problem and turns it into, or takes a gnarly matrix multiplication problem and turns it into just a like a modular arithmetic problem. It's kind of fun. Great. Okay, last thing that we have for this video is just a couple more definitions of things that are going to become really, really friendly later on. So we are talking about the transpose of a matrix. Transpose of a matrix is the thing that you get where you swap all of the rows and columns for A. I like to do that. I'll define it using double subscript notation. So if A is just the matrix Aij, then A transposed with a little t in the exponent is Aji, where the Ij entry of A transpose is the Aij entry of the original. What on earth does that mean? That means, okay, 1, 1, it stays 1, 1. But 1, 2, the first row and second column becomes 2, 1, the second row, first column. 1, 3 becomes 3, 1. Yeah? And so on, right? 2, 1 becomes 1, 2. 2, 2 stays 2, 2. Well, becomes 2, 2, but diagonal stays the same, yeah? And 2, 3 becomes 3, 2. Like that. It is flipping it across the diagonal. Like that. Take whatever that diagonal. I guess I should draw it actually diagonal. it feels very random to care about something like that the first time you see it. But it's it's amazing how much symmetry pops out of just matrix theory um, when you introduce the transpose operation. And just do one more example. In the case where you have a square matrix, the main diagonal stays put, and the off diagonals all switch. They like reflect across the main diagonal like that. Okay. You can, for example, one application you can use transpose to define the dot product of two column vectors. So if I have two column vectors, you know, something like this, I want to dot them together. Like we know what the dot product means, but if you wanted to phrase it in terms of matrix multiplication, what you can do is take U, the first one, transpose it. I wish I could flip it, but whatever, transpose it. And then do matrix multiplication in order to do the dot product of these two vectors. You transpose one of the two, if they're both column vectors, you transpose one of them into a row vector, and then do matrix multiplication of a row matrix and a column matrix. It's an alternative way of thinking about the dot product. Okay, and now I have one last definition for you. What is a symmetric matrix? A matrix is symmetric if it is equal to its own transpose. In other words, you just kind of like, okay, delete the diagonal, and then look at the mirror reflections. They should all be the same. Yeah, these are all symmetric matrices. Or these are both symmetric matrices. Okay, has to be square, obviously, in order to be a symmetric matrix, because if not, how are you going to end up with the same matrix, right? It'll swap the number of rows and number of columns. So if you want to get the same matrix back, at the very least, it has to be the same size, right? So it already has to be a square matrix, same number of rows as columns. Great. Okay, so that's all I have for this video. It was a very gnarly introduction to matrix operations. Again, there are a lot of examples in the book, so I highly recommend going back and reading it if it seemed like some of these were a little bit fast. And as always, post some questions in the Discord if you have them. Next time we'll be doing some matrix algebra, so just more development of the theory of matrices. And I will see you in that video.